Welcome back. This is going to be homework number 4 for fluid mechanics, part A. Part A's problem statement is asking to derive an expression for the optimal flow velocity in a pipe, assuming an annualized cost of Cc times d times L plus Pc times m dot times F L over d times v squared over 2, where Cc and Pc are constants for annualized capital and power cost respectively. Here D and L are the diameters and length of the pipe. F is the friction factor, m dot is the mass flow rate, and V is the average cross-sectional velocity. And then at the end, explain how it could be that the optimal flow velocity for water in a pipe has consistently been approximately 2 meters per second over 100 years. Alright, so the first thing I'm going to do is write down our annualized cost equation. So here we have our annualized cost, and it's going to be equal to the CC, which is our annualized capital, multiplied by the diameter times the length, um, plus the PC, which is our power costs. So power costs, and we know this is in dollars per year. And our power costs are going to be multiplied by the mass flow rate, which is m dot, times watts over kilograms. And we know that our mass flow rate is kilograms over second, so the kilograms cancel out, and this term ends up being watts over second. However, we need it to be in years, so we're going to multiply this term by 600 seconds in an hour, 24 hours in a day, and 365 days in a year. So now I'm going to draw a diagram of the pipe we're looking at. So we're going to have a pump on one side, and our pipe will be laying on the ground, so no vertical movement, with a output the same as its input. So let's say 20 meters per second. And now that we have our pipe, we're going to write down our Bernoulli's equation, which we have memorized as our injection work, which is delta P over rho, plus the potential energy. So we have our G constant times Z2 minus Z1. However, in this case, since it's flat, this just goes to 0. Plus the kinetic energy. So we have our V2 squared minus V1 squared over 2. However, these two are the same, so this also goes to 0, which is equal to the negative of our friction work, so big F here, plus the non-flow work, which is WNF, our mass flow rate. And for our situation, this entire side will go to 0. So we have our frictional work being equal to our non-flow work over mass flow rate. And the units for this are going to be watts per kilogram. We know our frictional work factor is going to be equal to the Darcy friction factor, so we get, let's see, we have small f length over diameter, v squared over 2. Rewrite our annual cost equation that we are analyzing. So we have our annual cost equals Cc times L over D times L times D plus PC m dot times our friction factor because of its units, which is going to be F L over D V squared over 2. And now looking at m dot, we can So m dot is going to be equal to the density of the fluid times the area, which in this case is going to be pi d squared over 4 times our velocity. And rearranging this equation to solve for velocity, our velocity will be equal to m dot times 4 over rho pi d squared. And now squaring our velocity in order to substitute back into our annual cost equation, this will be equal to 16m squared over rho squared pi squared d squared. And now we can substitute back into our annual cost. So let's write it out again. Annual cost equals our CC times the length times diameter plus the power cost times our mass flow rate multiplied by our friction factor, so FL over D. Substitute the V squared in, so we get 16m squared over rho squared pi squared D squared over 2. And now taking the derivative of our annual cost with respect to the diameter, we will get CC times L minus 8 PC times m dot to the third power FL, all this times 5 over rho squared pi squared d to the 6th. And then solving for our D optimal, we get, which is this D right here, we get 40 PCF over CC rho pi squared to the 1/6 times our mass flow rate to the 1/2. The optimal flow rate for water is roughly 2 meters per second. And so we need to relate the flow rate of water back to its velocity. So we know that our mass flow rate is equal to rho pi d squared over 4 times velocity. So we've already solved for our v with this equation, so we can copy and paste this down. And this is the relationship between our mass flow rate and our v. And how does this relate to our optimal diameter that we just solved for? Our d optimal that we just solved for into our v equation, and then solved for our v optimal, so our velocity optimal. So v opt equals 4 m dot over rho m dot times cc rho squared pi squared 40 pc times f all to the 1/3. And this is our answer. So that is an expression for the optimal flow velocity in a pipe, assuming an annualized cost of this. But how it could be that the optimal flow velocity for water in a pipe has consistently been approximately 2 meters per second over 100 years. This is due to inflation. So as the CC increases, the annualized capital increases, the power costs also increase respectively. So when both of these increase, they also get enacted on by the power of 1/3, and it keeps the velocity the same for over 100 years, which for water has been 2 meters per second. The only thing that can affect this is if the density of the fluid changes. So for example, air has an optimal velocity of 12 meters per second roughly due to its lower density.